All right, let's continue our discussion about complex numbers. Last time, of course, we saw that a complex number z can be written as, for instance, a plus ib, where a is defined as the real part of the complex number z, and b is called the imaginary part of the complex number z. And again, it's very important, the imaginary part doesn't have the I on it, it's just the number part, the coefficient. And what we ended with was kind of a philosophical way of looking at or trying to picture complex numbers. And this is not new, this isn't something very complicated, this is something we learned way back in grade school. When we talk about numbers, we were introduced to what's called the number line. And it was said that all the numbers exist on this infinitely long line, where right in the center we have 0. Positive numbers go to the right, so here's 1, here's 2, maybe here's pi over here, and so forth. All sorts of numbers, every number you could think of, all go to the right positively, and of course to the left we have the negatives. So we'll call that the negative direction. And this was called the number line, or now we will refer to it as the real number line, because of course we now have not just real numbers, but a new set of numbers called the complex numbers. And so it would be interesting and helpful to imagine the complex numbers not like some separate number line that we just call the complex number line, but rather to show that this whole time the number line was just one part of a bigger whole. So instead of it just being this one infinitely long line which contains all the numbers we're aware of, that's just one axis of a two-dimensional plane that we'll call the complex plane. So it's like we've gone from one dimension, a number line, to 2 dimensions, a complex plane. And the way we imagine it goes like this. We have our x and y axes. The x-axis we'll refer to as the real axis. The y-axis is, of course, the imaginary axis. And just like with the number line, on the real axis going to the right, we have all the positive real numbers. Okay, I'm just showing integers here, but of course decimals and fractions, every number that's real is put somewhere on here. And the imaginary axis is very, very similar, except these are all the imaginary numbers, the complex numbers. So we have I, 2I, and 3I, and so forth, and the same negatively, minus I, minus 2I, and so forth. And so now, when we go, select any random number, we don't just have to put this selection on the real number line, but it can be anywhere on this infinite sheet, this infinite plane. And so maybe I'd say this point right there. I want to know, what is this number z, this complex number? Just like if I look back at the real number line, I could say, what is this number right here? Well, you put a point on the number line, you see what is that point? That is the point 2. Well, here we put a point on our complex plane, and that refers to a number. This number is called z. Now, in this particular example, z would be equal to 2 plus 2i. Okay. You basically take what's the x-axis, what's the y-axis, and that gives you your number, the real part and the imaginary parts. Well, that's very nice and very helpful. So now what we could think of is this new number, these numbers we've been dealing with this whole time, including the real numbers, are really two-dimensional vectors in this complex vector space. That's the fancy terminology mathematicians want to use. That if I want to refer to a complex number, some random number, I could either think of it as a real part plus an imaginary part. Or I could think of it as a two-dimensional thing, a vector that points out into space, and where it points, the end location, tells you what this complex number is, what this random number is. And it's gotten by saying, well, how much is in the x direction? That's also called the x component of the vector. And how much is in the y direction, the y component of the vector. So the real part can be thought of as like the x component, and the imaginary part can be thought of as like the y component of a vector. And so now we could think of these complex numbers as like an x component in the real direction plus a y component in the imaginary direction. Okay? Now, of course, it's just a number. It's not really a vector, but this is just a mathematical manipulation to help kind of picture or imagine, or in the future, how to work with these numbers correctly, because sometimes it may be, as I said before, that doing mathematical operations with complex numbers may be different than doing mathematical operations with real numbers. In fact, that's definitely true of vectors. If you try to add two vectors together, you need to know how do you do it. And if you remember, if we have vector A, who let's say is A in the x direction, A I hat, plus B in the y direction, and vector B is some number in the x direction and some other number in the y direction. And I want to add these two vectors together. The way you do it is you add the x's with the x's, so A plus C in the I direction. And then you add the y components, B plus D. And that's in the y direction. And this will be our new vector C. And that's great. Now, here's the thing. There's another way of writing down a vector or symbolizing a vector that we've seen. This is the x and y component form, or the component form of a vector. We also know that vectors, some vector, can be thought of as a magnitude and a direction. Right? So if we have some random vector that points out in some direction, you could either think of, well, what's the x component and what's the y component? And then you'd have x in the x direction plus y in the y direction, and that is your vector v. Or you could think of it as a magnitude, that is the length of the vector, in a direction, theta, the angle that the vector points out in. So, if that's true of vectors, and what we're trying to do is represent complex numbers like we represent vectors, because we know vector math, so we could just apply it to complex numbers, is this also true? Is there such a thing as a magnitude and direction for a complex number? And indeed there is. A complex number, z, can be thought of as the real plus the imaginary part, or it could be thought of as a, let's call it capital A. This is like, or in fact, let's do R, just to keep the same notation for magnitude over here. R is the length of my vector, so this is what's called the magnitude of the complex number. And then something about the angle, of course. We need two variables here, a length and an angle, or an x direction and a y direction. But the way we're going to write it is very, very special. We're going to put the angle in this form. It's going to be the exponential e raised to the I times theta, where theta is the direction. Now, sometimes, and in fact, more generally, this is also called the argument. So sometimes when you're looking at math textbooks and things, you'll see the arg of z. basically means the direction, the argument. It's this number theta here. Now, of course, with vectors, these are the magnitude, the length of the vector, how fast, how long, how far, whatever. And theta is literally an angle. I'm moving in this direction, or I'm going this fast in that direction. Complex number, of course, is just a number. It doesn't have to mean anything about angles, and that's why sometimes it's just referred to as the argument. But of course, what we're thinking in our minds, what we're picturing, is this angle that this so-called vector, this complex number vector, points. Now the question is, okay, if we want to represent this complex number a plus ib in this new form of magnitude and argument, or magnitude and direction, how do we do it? So we have the point over here, and we say, okay, the x component, I'll call that a, and the y component, I'll call it b, for a plus ib, of course. And remember, this is a complex plane, but who cares? We'll just think of it as a vector. Well, my question to you is, if what I want is the magnitude r and the direction theta, how did we get it with normal vectors? Well, if you remember, for normal vectors, we saw vector v has a magnitude which is the square root of the x component of v squared plus the y component of v squared. Right? If I tell you, you go this far to the east and this far north, where do you end up? That was just a Pythagorean theorem. Remember, we could just think of this as like a right triangle here. If I want the magnitude, this r, that's the hypotenuse. So I need the a squared plus b squared equals c squared, and that's how I got the magnitude for my vector. And indeed, that's also true for complex numbers. R, the magnitude of a complex number, is given by the square root of the real part of your complex number squared plus the imaginary part of the complex number squared. Okay? Very, very similar. X squared plus y squared is the magnitude, square rooted, of course. Well, for a complex number, the x and the y refer to the real part and the imaginary part. And likewise, if you remember when we did vectors, we want this angle theta, and what we know is the x component and the y component. Well, the angle theta is given by theta is the inverse tangent of the y component over the x component, in this case, in all cases. Well, that's also true for the complex numbers. Theta, the argument of our complex number, is the inverse tangent of the imaginary part over the real part. And so given a complex number, a plus ib, if we want to rewrite it in this new exponential form, complex exponential, then we need to find the magnitude. So it's, in this case, z is the square magnitude of z, square root of a squared plus b squared. And our theta would be the inverse tangent of b over a. And of course, we'd have numbers for this in a real example. We plug those numbers in, we get numbers, and then we could say z is our magnitude, the square root of a squared plus b squared, times e to the I, and our theta is whatever this tangent minus 1 of b over a. Okay, this looks super, super messy, but it's only because I don't have real numbers sitting here. If I plug numbers in, these would just be numbers. They wouldn't have this long, complicated look to them. But this is very important. And in fact, what you see a lot of times with complex numbers is the complex exponential form more often than the normal real and imaginary part form. Just because, number one, it's more compact, it's quicker to write, and number two, exponentials, just generally in mathematics, are very, very nice to work with. They're definitely nice to work with calculus, but it's true in all sorts of math. So you see the exponential form a lot. Now there's something else we need to talk about for this complex exponential form, and it goes to thinking about these things in terms of angles and magnitudes and things like that. There is a relationship that says e to the I theta can be rewritten, instead of exponential stuff, it can be rewritten as trigonometric stuff. Because sometimes trigonometric things are easier to work with, or maybe they do some of the math better for you, or whatever. What it really lets you do is kind of separate the real and imaginary parts when all you have is this complex exponential. Well, this complex exponential is equal to cosine theta plus I sine theta. They're the same thing. Obviously, the left-hand side is much more compact, faster to write, and the right side, not so much, but more people are comfortable with trigonometry than they are with exponentials. Another thing, like I said, if you look, here you have a real part, and here you have an imaginary part. And so what tends to happen with, more complicated problems, let's say in quantum mechanics, every equation you work with has a bunch of complex numbers all over the place. But it's at the end of the day, the answer you should be getting when you want to check about an observable or something like that has to be real. You're not going to look at a particle and say it's moving with this speed, and the speed is not a real number speed. It doesn't make sense to have an imaginary number speed. And so what tends to happen sometimes is we use complex mathematics because for some reason it's easier to do it this way, but then only we filter out all the imaginary stuff and we only keep around the real parts. And so this is very helpful when you're doing these things, because what you can do is look at your final answer, which may be a big long line of a bunch of trigonometric functions all over the place, and you just keep the pieces, the cosine pieces, let's say. Or if you did derivatives, maybe the sine pieces, because the imaginary parts switch. Now, of course, with this, there's another one that's very similar, and it says e to the minus I theta is cosine of theta minus I sine theta. Okay? So two little relationships, very easy. If you know one, then you know the other. You just put the minus sign on the imaginary term, or the positive sign on the imaginary term. Now, I'm about to give you the finished product of a problem I want you to do for homework, which you'll see when I post it, and that is write the trigonometric functions in terms of the complex exponentials. So what I've done here is I've started with the complex exponential and I rewrote it as trigonometric functions. What I want is the opposite. I want to know, how do you write cosine theta using complex exponentials? Or how do I write sine theta using complex exponentials? Because if it's true one way, it must be true the other way. So I'm going to give you the result, and what I'd like you to do for homework is show the work of how to get this result. How do you prove this is true? Well, here's the result. It turns out that cosine theta is e to the I theta plus e to the minus I theta divided by 2. Okay. Sine theta happens to be e to the I theta minus e to the minus I theta over 2I. Very similar, but you have to be careful about a number of things. The negative signs, but also this I sticking around for the sine piece, which makes sense because if you notice, on the other form, the I is sticking on the signs. So when you do the sine, you should imagine there's going to be I's involved. But it's a very easy way to do it. I'll give you a little tip how you want to start it. Is if you notice, cosine theta says you're adding these two exponentials together. So obviously, maybe start by adding these two terms together. E to the I theta plus e to the minus I theta is going to be this right side plus that right side, and see what happens. And then you simplify, rearrange, whatever you have to do. And likewise, the sign has this minus sign, so I'm subtracting. So maybe I subtract these two terms, which means I subtract the two right-hand terms. And again, see what you have to manipulate, see what you simplify, but you should get these two results. Right? So that's complex exponentials. Obviously, there's a lot more to it when you get deeply into the mathematics. But for our purposes, these are the things we want to know. Number one, there's such a thing as the complex plane, where you can have vectors that point out in whatever directions. The magnitude and the direction of these vectors tell you about the real and imaginary parts of this complex number. The mathematics, how you add two complex numbers together, turns out can be done the same way you add two vectors together. It says that these two vectors are not in the x and y directions, they're in the real and imaginary directions of this complex vector plane. So we wind up with a magnitude and a direction, or also called an argument. And then we have very, very fancy representations of how to go between trig functions with complex numbers and complex exponentials. And these things are super, super, super important and very, very nice tools to use when you're working with some more complicated problems. It makes the mathematics easier. Because it might be that you have some integral you need to solve that has a bunch of trig functions all over the place. Well, if you turn those trig functions into complex exponentials, all of a sudden the integral of an exponential is so much easier than the integral of a trig function. And then you can always go back. So you transform it into complex exponentials, you do whatever math you want on those things, whatever your result is of there, you transform them back into cosines and sines and so forth. All right, well that's it for this particular lecture. That should finish up our complex number stuff. I hope it's clear. If you have any questions, of course, let me know. I will see you next time.